So in the last session, we discussed about the first chapter from this classical mechanics, the theoretical minimum book. And in this video, we will discuss about the second chapter. So, and this is going to be very brief, as you might have seen when you clicked on this video. This is just about motion. So now we have discussed, just to recap, classical mechanics is deterministic, reversible, and even though deterministic, it could turn to be chaotic if there are too many variables involved, or it could be unpredictable even in that case. And it is continuous. It's obviously dynamic, and yeah, so those are the properties of it. I would like to get into the motion. Now, motion is easily discussed in terms of a particle. Because nothing is actually like a fundamental particle. Even an electron is not a particle. Electron is composed of smaller particles called I don't know. There are some even more fundamental particles. So literally nothing is a particle, but we just take even Earth as a particle. When we want to discuss about planetary motions, it just makes calculation easier. So in motion, take let's say we're discussing about a particle and it's trying to move somewhere. Now the particle obviously has positions, and let's just say position, we specify position by x, y, z coordinates. Obviously it will have all those. They all change with respect to time. So at given time t, what's the position? So that would be denoted by this. So at time 2 seconds, its x coordinate would be like somewhere like around like 4. The y coordinate would be maybe 0, and z coordinate also 0. And similarly, so position can also be thought of as a vector, and a vector. So now just to recap, there are tensors of all. Tensors of 0 dimension would be called as scalar. 1 would be as vector, and 2 we can call it as matrix, and of n it's like n tensor. So and so a scalar doesn't have any dimension, so it doesn't have any direction. So I'm sorry, so a tensor of 2 dimension, you can correct it. Yeah, so tensor of rank. So this would be called as rank dimensions. So yeah, so this entire thing you can call it as a vector. Let's say R. You can write it as R. So this R vector, R bar or R direction, it gives the dimensions x, y, z at time t. Now, the job of classical mechanics is to figure out the position R of t from some initial condition in some dynamic law. So now let's try to figure out the so as the position changes, there will be some displacement. As particle moves, the delta that the particle has moved, let's say it has moved here. So what is this delta? So let's say delta R. delta x. So how much it has moved x would be t with delta t. So like with that extra delta time, how much it has moved? Minus x of t. So it will give you the delta in x. Similarly, y. And similarly, z, z or z. So you can just denote it in terms of r as of delta in r equal to r t plus delta t minus r bar t. So now velocity would be just velocity of that, let's say in x position, be just the rate of change of position x with respect to time t, and as time tends to 0. So as time tends to 0, so velocity would be just the rate of change in position with respect to time, and acceleration is just rate of change of velocity with respect to time. Now you may have all studied that. Let's just talk about the like how we denote this. So this we can count as dx by dt, and we can denote it as x dot, like a dot on the upper side top. So similarly for y dot and z dot. So and so a dot denotes it is a shorthand for taking the time derivative. So a dot on top of something denotes time derivative. Means basically it's same as that d that by dt. So now, so in short, instead of writing the all coordinates, we will just write it as vi equals dxi by dt as xi dot, and in terms of directions, we can write it as d r direction by dt. It should be just r dot r bar direction. So now the magnitude of the velocity, it has a magnitude just like Pythagoras theorem in 3 dimensions. So vx square plus vz square. This would be called as speed. So whenever speed is scalar, remember that. So this is speed, and this was velocity. So it's called speed. Speed is just velocity without the direction. So this magnitude rips out all the direction aspect of it. Now acceleration is just rate of change of velocity with respect to time. So it's kind of like rate of change of position with respect to time. So it's a double derivative of position. So it's vi or xi double dots. Vi single dot or xi double dot. So now we could take like an example, and so let's say there is a pendulum, and the particle only moves, the pendulum only moves along the x-axis with respect to time. All the other axes remain silent. So the position function is given like this: sine of omega t. This is a lowercase Greek letter omega, and it's constant. So this is the position. If that's the position, so what would be the velocity? Well, the velocity would be, since we don't since we don't want other coordinates, we'll just take x coordinate. So rate of change of sine omega t by t. So that would be just cos omega t. So when cos comes out because of the chain rule. So in order to just let me just do it properly. So this would be scheme written as so because we are using chain rule, we have to use first yeah. So we have to first do sine omega t divided by d of omega t times d of omega t divided by dt. So this is the chain rule, as you all know. So this cancels, but that's not how we do it. So what is would be that? That would just cos omega t, and this would be just omega t. So that's the answer. So omega times cos omega t. That would be the velocity in this case. Similarly, acceleration can be calculated as minus omega square sine omega t. So remember that the phase. So like if you were to draw a diagram of position x of t, let's say the position is like this, and pi by 2, pi, 3 pi by 2, 2 pi. This is just theta, the angle. This is 1, this is minus 1. So since it is just like a sine function, this is a, so it would only take 1 and minus 1. Velocity would be just out of phase by exactly pi. So I mean exactly pi by 2. So which means 90 degrees, because it's rate of change, right? So it is a rate of change of only 1. So be just out of phase by pi by 2. So whatever it was at pi, it is at pi by 2. So yeah, so 1 minus 1. So similarly, acceleration is out of phase by, so this is like I don't know, out of phase by pi by 2, and acceleration would be out of phase by pi. Similarly, so this is like short form of similarly. So it would be out of phase by pi. And if we were to go, well, the author in this textbook that I talked about gives another example for motion, the circular motion, and if you could technically go into that. So let me just take another example, or you could just give it as a homework. So it's similar to this. So we just take the function of the position and then derive it once, you get velocity, function of velocity, derive it twice, you get, or derive the whatever you got from the velocity. Again, once again, you get the you get this one, acceleration. So yeah, so that completes this chapter. It's relatively short. Motion. We talked about position, velocity, and acceleration, and not much else. So the later chapters will go much more into the theoretical minimum stuff. So goodbye.